Если можно выполнить, то, конечно, не надо уточнять. Я допустим, ты что не может.
Что такое конформная теория поля? Можете еще раз имеется в виду, что Лагранжан действие, ну, может, не самое Лагранжан, действие.
The title is by a category of Landau-Ginzburg model via Witten equation. Okay.
So, thank you for the introduction. I'm happy to be here. Thank you for the conference president to invite here. I remember that more than 10 years ago, I was invited by first Huijun Fan to be here. And time I also speech. So today I will talk about category of Landau-Ginzburg model, Witten equation. And this is, in some sense, old story for me. Let me introduce a quick of so this is well known because of the homological mirror symmetry conjecture. Corresponding to the closed string theory, conservatory proposed the HMSC of open string in 1994. He conjectured that A model is a geometry about Lagrangian sum manifolds, which was later described by Fukaya category, and the B model is a geometry about the complex sum manifolds, which was described as the category of coherent shifts. If two Calabi-Yau manifolds are mirrored to each other, then the two type derived categories should be equivalent. So here is a global picture of homological mirror symmetry conjecture. So you can see the original one is from the A theory to the B theory. So the up one. And so the A model side is the Fukaya category, and the B model side is the category of coherent shifts. But then people realized we should this mirror symmetry should contain the so-called Landau-Ginzburg model, because in string theory there is also n equals to 2 supersymmetrical Landau-Ginzburg model. So this will gives the bottom line mirror phenomenon. So one should compare the A theory in the A side related to LG model to the B theory for LG model. So the B model side, people can think it as category theory or for matrix factorization. And in the A model side, there are two approaches to describe this category theory. So one is one exists for a very long time, the so-called saddle category, because people can consider the LG model as just vibration over a complex plane. So this is one idea to construct the higher category. Another approach was studied by me and two of my students. We try to describe this category in terms of the Witten equation. So here I list some important progress for HM. So you can see in the early time, much work. So in 2004, for sure. Awesome. And in a variety case, higher and say space. And then there is some proof by Savage Suleiman for the SYZ goal operation case. And so there are some recent work by like Witten. Also, I listed some most recent progress along this direction, like Huijun Fan and Sheridan and Smith. So these are the progress in the proof of geometry. Today, what I want to talk about LGA model. The study of the LGA model has its own significance, which was conjectured to be related, which studied the following papers. So the first paper was written by three physicists with the title Algebra of the Infrared. String field sequential structure. Let's see. Then this paper has been translated in this algebra of the secondary force. In this paper, the three physicists found the so-called algebra structure, and then from Savage and Suleiman realized that this will of some virtual structure generated from the study of the second of mind points in the comments. Second, they analyze this projection. For any dimension, they can generate infinity. In these two papers, they also have the conjecture. They proposed to study the model of the so-called Z-extended equations, which turns out to be the Witten equation in Fukaya theory. So this is open version. In another words, people should study this first order elliptic equation with boundary variable. So this being carefully studied in this paper, 2018. We found them to very high. So then I will introduce to the problem. We define what is called the time LG system. The LG system consisting of three is n-dimensional complete non-compact scalar manifold with small geometry and the scalar form omega is exact. So in most examples, average in F is assumed to be Stein manifold. And that W here is a homological function of F. But in all paper, we only treat the most case. Because for the usual homogeneous polynomial, you can't see, you can find the very simple hidden in the symmetry. So we need a couple with the polynomial with symmetry with the usual most homological. Then, with respect to this telemetrical edge, we have the time connection level. So here, is that the definition? All the definition is so actually is the telemetric. So with respect to this telemetrical, we have the unit metric connection. It's called the time connection. The typical the 0, 1 part is just the Cauchy-Riemann. And then this system is called satisfy the frame condition. If there exists point, the constant C1, C2, such that for any point, fine. So I write it in this complex form in F. So should satisfy the three estimates. So the first one says absolute value of W, and also the absolute value of the second derivative of W should be controlled by controlled on the upside by C1 times this distance of I to 0 times with log the first derivative plus the constant C2. Second, this is recent. Distance increasing. And the second one says less than for this the first derivative, we should be control this exponential function. So these are technical conditions to run here. There's no grow up phenomenon when we treat that Witten. So here is W, we have only generated other continuous polynomial or Cn with each weight Qi less or equal than 1 over 2. The W with total weight 1. That W0 is weight more than 1. Assume that H is a kinematric from Cn, which is a compact equation of the Euclidean metric. So here we don't take the Euclidean metric. We need to do a compact equation. Then this system satisfies the frame condition. For example, we can consider the critical polynomial defined of C5 with this standard Euclidean metric. So this is a frame system. And of course, we can perturb this standard metric with a compacted help. Okay. So for the category, we should describe the object in the category. So it's not like in the higher side of category, people I mean usually discuss vanishing cycles. Here, for object is symbols. The Cantor form omega as morphism will tilde from the tangent space to the cotangent space. So you can use this as morphism, take a smooth function h f, and that magnitude is a gradient of h with respect to the Riemannian metric G. We have the Hamiltonian vector field. So xh is a Hamiltonian vector field of h. It's defined by the image of W tilde inverse of EH. This equals to minus the complex structure X on this gradient vector. However, we have more refined isomorphism because here we not only treat the real case, we treat the complex case. So omega tilde actually gives a more refined isomorphism. So it maps the homomorphic tangent bundle to the 0, 1 cotangent bundle. So vice versa. So this is very important because you use this isomorphism, you can find this vector field lines on the homomorphic vector field. So it's an image of this function. Also, we can complex conjugate. This decomposition should use a real part to generate Hamiltonian vector field X. This vector field is splitted. So XW plus its complex conjugate. And then also we have the decomposition for the Hamiltonian vector field given by the imaginary part. The following relations between the vector fields. So you can see Hamiltonian field of real part of W equals to minus Jx acting this Hamiltonian vector field. And also this Hamiltonian vector field of real part of W is just the negative gradient flow of the imaginary part. So we have two equations. So the first equation, we can consider the Hamiltonian system of the real part. So this equation, phi dot k equals to this vector k. And this system is equivalent to this one. So in complex form, this equation can be written the following. And the second equation is, of course, this equation also the equivalent to the negative gradient flow of imaginary of W. So those two equations are equivalent. So besides this equation, we can also consider the negative gradient flow of real part. So this is a equation. So use this equation, we can generate a diffeomorphism one time P or P dot y. So this flow gives the definition stable manifold Cp plus and the unstable manifold Cp minus in the following way. So the stable and unstable manifold related to some breaking point P. Cw is assumed to be the set of integral points of W. So you see this unstable manifold Cp minus is defined as a set of 4 points Q, such that Q dot T goes to P as T goes to minus P. And also we have the definition for CP points. So those are the objects in the Fukaya. And CP minus and CP plus are called Lefty symbols. Similarly, we can from them we can also define the Lefty symbol in this way. So this is that Lefty symbol rotates in CN. So those also are the objects in the. And then there is a simple analysis that P be a critical point. Then we can take any point Q in on the unstable manifold. Then W, the imaginary part of WQ equals to imaginary part of WP. So that means that this quantity gives you invariance on the unstable manifold. And because the flexible manifold is defined with respect to the negative flow of the real field. So we have such relation. Is less or equal. So this context is appears in the previous talk. Switch story. See. CPM repeats something like negative because they are diffeomorphism for the stable space on the tangent space on the tangent space of the key.
That's your T plus.
Yes.
It's just
It's X in some sense. Now we can see the linear equation. So here we can see the negative gradient flow. But then we can see the equation of a real part. But this equation is just the negative gradient flow of the imaginary part. This flow gives the time t diffeomorphism by t, and we can take two critical points, P0 and P1, with the following condition: the imaginary part of W of P0 should greater than the imaginary part of WP1. So we denote by L0 to be the unstable manifold with respect to P, stable manifold with respect to P0, and L1 equals to the stable manifold with respect to P1. So here I draw a picture. So here is the this is M. And of course, there is a simple lemma. So under the prime condition, the lemma makes sense to the whole. This is to plane, and we take two critical values. So this is zero, and this is J1. So I put here. So this is zero. This is so the negative gradient flow of digital is looks like the following way. So from
sorry, same question. These points, in picture they don't look is zero at the point.
I mean,
This point.
this is
Is L0 smooth at the point?
because it's a homomorphic, it's most homomorphic, and then this is a smooth. This is smooth. Usually, if it's not assumed once. This that is. That's that also. Okay. Okay. So you see the pool mechanism the card is to discuss solutions. And then the point is we use this flow move to zero. Yeah, and the such that it intersects with one. So in other words, we consider a path move by this flow to so here is a definition for it. We say that L0 intersects transversely with P if and only if adjacent matrix the phi P of L0 intersects one transversely. If L0 intersects transversely with L1 at time 1, then we say that L0 intersects transversely with L1. Of N is to perturb the scalar potential such that L0 intersects transversely with L1 at generic time t. So this is a first. So perturb. So if you want to perturb the metric, you need to find a suitable parameter space to perturb in this parameter space. So take a function, a smooth function of f. We can define the C0 norm in the usual sense. And then we take a rapidly decreasing sequence. Epsilon goes to 0. We can define the following norm. The norm epsilon defined is defined as the sum of epsilon k to the power k times the norm of the base derivatives of phi. Then it can be this space. So usually this space is only a Fourier space. It's not a group space. But we can show that this is Banach space. Of course, here one should assume that is not compact. For example, in our case, we should consider the small space consisting of the function so with compact spots, and then we can complete this subspace in with this form. Then we get subspace C infinity C epsilon. This space is then we define the potential space H consisting of this function phi with a compact spot such that omega phi equals to omega plus phi function of greater than 0. So phi is supposed to be the potential. We use this potential to double the original scalar. This is open convex in this number space, which can be considered as a boundary manifold. Whose tangent space phi is just this space with norm. We consider a small space GL. Here GL is defined is related to the to L0 and so we take two Lipschitz symbols. So one is M0, the other is L1. So we will define the closed subset GL such that consisting of the function phi in this space. But there is an extra condition says partial phi when restricted to this region there. And then we don't want this calculation to be so large. And we take a small mu and we define G mu L. So this is a set of phi in this space, but with the extra requirement, the norm of this quantity should be less than mu. So this property says the calculation is very small and to the original data form. So we the following server, the so-called professor in section server says that MH will be a time LG system. There exists small mu zero such that for any fixed mu in this interval, 0 or mu zero. And for generic metric G tilde in this space, and the generic T, L0 intersect transversely time T. This is a transversal section. You know, the set of time one flow lines of phi T from L0 and 1. Then we have this set because it's intersects transversely. So this set is finest.
To one time T.
And time T is because you have so at any time T it gives a diffeomorphism. This diffeomorphism bring 0. And for generic T means T in the R topology. T is defined from the positive line. Generic means in this. Yes. Because we don't know the condition. And condition says and is the first one here. In the infinite far place, we are grow relatively. So that means in a very short time, in the infinite far place, there's no so we have spatial space. So we have done two. So the first calculation is we intercouple the Taylor form such that the two Lipschitz symbol intersect transversely. This is the first step. The second step is we need to have the real part of W. Yeah. So we have another calculation. So this is defined in the following way. We consider the smooth function defined on unit times n. So this smooth function is an extra limitation. Along the flow lines on SW, this is parallel. What does this mean? Yes, if we consider flow lines, flow line from this part or to this part, we don't handle the region here in this function. So we keep it its power. And then we can define this norm. This norm is defined as supreme of the norm of first derivative of omega phi, and plus the supreme, the norm of second derivative. And then we take a perturbation in this parameter space. We consider the parabola Hamiltonian equation, this Hamiltonian equation, but we replace the real part of W by this one, of H tilde equals to real part of W plus very small equation. And then we have the following lemmas, that there exists epsilon 1 such that for any omega bar in this calculation space with a small norm, and then the intersection, the set of the intersection set is the same, because we only perturb this part away from the flow line. So this will keep the number of the section lines. Okay, so we studied the Witten equation, and so Witten equation can be defined by the following actual function defined on this path space. So the path space is a map. Is a curve starting from L0 and ends at L1. So this is a smooth path. And then on this space, we can define the output metric. Because you can go to a variation of this one, and then you have the vector fields attached to these flow lines. So you integrate the inner product of the two vector fields. In this way, you define the output metric on the path space. So on this space, you can define a one-fold cosine related to this Hamiltonian function. So it's defined in the following way. So for for the express in symplectic geometry, this is known. And then you can consider the covering space of this space. You fix one base point. That means you fix one reference flow line curve. And then we found the pullback of this this closed one-fold is exact the covering space. It's equals to d of some action function ah. This action function can be written in the following equation. So phi is the path connecting L0 and L. So in this picture, in this picture, this is zero is a point. On the path space, and the L1 here is also a curve, but it's also a point in all this space. And then you consider the path connecting L0. So on the path space, you consider a path from L0 to L1. But in this space, this is just a strip. This is a strip connecting L0 and L1. So this is our actual function. And the we study the autonegative gradient flow of this actual function. It turns out it is given by this map, from segment to L. So sigma is the infinite long strip. R times 0, 1 satisfies the following equation. So the equation, the boundary value data is given by we require the strip maps to so here is our strip. So we require this part is not this boundary, and this boundary is less. And in the when the strip goes to minus infinity, so this part should tend to the flow line. The flow line here, but you can see on the image. So let's see. When s goes to minus infinity, so this the map should approaches this group. This is a boundary value problem. So if we assume the perturbation term equals to 0, then it becomes the Witten equation is Lagrangian boundary value as follows. So in context form, the Witten equation can be written in this way. And we can also define the energy related to this Hamiltonian equation in the usual way. So here is find the smooth solution of this equation flowing from L minus this flow line to L plus in this set. Then the energy has a following identity. The energy of phi equals to the actual function of these elements minus the actual function of the minus of the elements in the mass. So here phi plus is a strip. It's a map phi plus joint with this. We can let phi from sigma to m be a smooth solution of our Witten equation with a boundary value data. Then the following three conclusions are equivalent. So the first one says the energy of phi is finite. So the second one says the solution of the perturbable Witten equation to satisfy the asymptotical behavior. So when s goes to plus infinity, then this solution should asymptotical to L plus. So vice versa, if we consider s goes to minus infinity, we have another asymptotical behavior. So the second condition says the convergence condition is equivalent to this exponential decaying condition. So the three conditions are equivalent. So this is nothing surprise because it's a routine proof in geometry. And then we consider the model problem, the compatibility. For small mu, we can fix the metrical G in this potential space, and we choose the perturbation omega bar. We consider two flow lines in the set of SW. So L minus and L plus are flow lines from the left symbol L0, L1. And then we considered modular space, this modular space. The modular space consisting of solutions which satisfy this boundary value. And also the limit limiting conditions. So this is our modular space. So we define M tilde to be the modular space of solution this equation, which have a finite. Here comes the regularity theorem. As if P greater than 2, then any W1T solution of this problem is in the space C infinity. It says this is a smooth solution. And then we have the very important compactness theory as follows. It says if the advection function omega bar, this quantity, if this quantity is less than 1, then for any solution phi of the omega bar at level of the Witten equation with finite energy, the following comes. So the following estimate says the maximum of the gradients of W can be controlled. And also D phi and so D of D phi in this distance is less than C. So that means this solution can't go in or out. It can be only restricted to some computers. Here is a very brief introduction to the proof. The proof is rather complicated. The proof of C0 and C1 estimates, but again, they depend on each other because here we can't use the blow-up analysis. So we have used the following facts. Is the time condition of W. And using the time condition, we can show this distance function is of W1, 2. But it's defined of the two-dimensional strip. And then, because it's two-dimensional, then we can use the John-Urban inequality to show this, the norm of gradient belongs to a LP space for any T greater than 1. And then we can use the bootstrap estimate to get the interior estimate. But near the boundary, for the boundary C0 estimate, we need 2 types of isoperimetric inequalities. And also we need some scaling analysis. So the proof is rather complicated. I skip it with just to the basis. And then after that, we can define the law of origin of the model. We can give grading for the flow lines in the set of W. This is given by the slope. And then we define the complex. We can take a coefficient ring, for example, and so on, with space generated this. And then we define the boundary function from this flow lines to this flow lines is defined in the following way. So you take a flow lines from L0 to L1. We denote it by L minus. And then this equals to the final sum of L plus with the coefficient here. Coefficient here is to count the number of solutions and count the solutions from L minus to because we can calculate. Because here we can we have a very detailed analysis. Says so this space is so here is M tilde. M tilde of L minus L plus is a modular space of solutions of the Witten equation connecting two flow lines. And M here, because that is asymmetry, you need to modulate the asymmetry. So you get this modular space. And then you can show this is with zero dimension space. And then because you have compactness result, you can count the number of this finite set. So this is defined in following way. And then using the grammar for compactness deduced a uniform local compactness theorem, you can prove that partial square equals to 0. So it forms complex. And then we can define the flow in the usual way. So here are also some technical difficulties. Because you have to show, you have to calculate the dimension of this. So the first step, you need to show this is a proof manifold. And then you need to calculate this dimension. So you can use some Riemann law. The boundary Riemann laws dimension is just the difference of two Maslowian index for the flow lines. And then you need to show modular space is arithmetic. So here it is simple because the function symbol simply connected manifold and it has a pin structure. So this shows the modular space is arithmetic. And then you need to use the modular technique to show that flow homology is independent of the choice of generic calculation. This is a really way. So unusual proof is proof for comparison. This is it's going. This algebra. We just imitating the higher side of construction. We can construct the infinity category as follows. So this is a C-linear category consisting of the following ingredients. Objects are the Lefschetz symbols with respect to the critical points of topic. Morphism space defined by the complex. And then the compositions mu s is defined in the following way. It's so your input s flow lines. So Li is Ly in this home space and Ls in this home space. So you input S, the flow lines, and then your output you get 1 L0. But here you also is the modular part. So the modular problem here is you need to consider the boundary value problem, not only with two boundaries, with several boundaries. So you consider this one. You can take a distance and with some puncture points. Usually this is with several with S+1 symbol. Zero, you can see from the image. So in the image, picture is see the so here is sure. So this will go wrong. This is you can see the fun. So this is consider the output. Output flow line for L0.
Is it little L0 there?
L0 is here. Over. So we can see that.
M. L1 times L1.
So here, that is L0. So the model space and also the solutions of some Witten equation with S+1 boundary conditions. Sure. This is very important. We need extra logic section of logical form. So yeah, because in some sense it's a stem. So that exists locally. Then use this section bundle. We can define. If you read it, you can model. Expose that way. Model. So this was proposed by what was the relation pregnancy after so in that sense, we need to generalize the survey with some object version. So it's called version of package. Then future. So the definition here is very much.
So, to achieve the transversality of Lagrangian, you deform a scalar potential. Then you deform a scalar symplectic. So resulting category A depends. So it is not invariant. It may not, but you said that it is variant under the function.
Yeah.
want to deform a simplex structure itself. So I'm wondering that resulting category may depend on
So it's conjecture. But
picture.
and topological.
If we don't start from transversal cover.
We need only transversal. So it's the water. Oh, yeah. Oh, it's
Yeah, but let's give the shoe a
assume it's
shoe
ratio
after part of it. Okay.
in the second. And it's a finite. So something on this fact. That's amazing. I have to say, this very this is then you so what's but there's no
There are many choices of genetic.
that's true. It's so into form complex. We don't deform. Then why
Oh, why?
then why have chosen not to? Rather, that's the interesting thing is because we need to keep it. This is my original idea. You have two choices. One is for you. Try and see. Okay. Something like yes. Why then?
You
I'm so regrets. Before I complex structure doesn't work. If you post in more or less is the same. It's the same. Because if you are default complex structure, if you have one parametrical of the linear of unique X metric defined nearby. So this is an equivalent for going forward. Yes, once. Then why don't you? This is how we thought. This is a current.
on the left. There is thank God. Second polyton body. So what is the mirror of
Again is the mirror is in some sense you can separate the story. One is you can consider the mirror. the model mirror to the B-model. And so those two theories should be related to some combinatorics described here. Because you have the critical variables. Critical variables. And then this is a final point. You can see that so and then you can see the second. So in this way, you can get the combinatoric A infinity structure or L infinity in combination. So it's conjecture that I think there's a couple of those taken. There's when combining with some coefficient system. So that means we should combine the geometrical structure here, formation here, with the combinatoric structure here to provide some equivalence. So the category you get should be the deformation for icon. Yeah. So this was the text. So the first step is we need to construct this kind of model.
Your assume that W. In order to get show the concept, the last concepture, I think, or I could, you need to remove that.
No, it's called mass. So
Yeah, in that case, you need to consider big range.
that's true. That's true. That's the better. If you say also in the papers. Assuming is was. Of course, if you need to train the neuron, you need to consider the symmetry. Symmetry actually group. Actually, is the two code.
Yes, so usually, so
as it shows.
maybe here. So we'll speak again. So on detail, we resume at 4.
카테고리